All right, so let us finish very quickly what we're talking about last time. Basically, the part one of cosmology. It was just introductory remarks, and then we'll start with the cosmological perturbations. So what we saw last time was the Friedmann equations, the stress and intensity being perfect fluid, the equation of state, and depending on the equation of state, you can solve the Friedmann equation and you find various expansion rates, both in terms of, say, in terms of proper time. And then I was just telling you about this brief history. So this is the part one, which is introduction still. So I was just telling you about the brief history here. And as I said, this is sort of important to keep in perspective because you learn various things in classes and books and papers at any given time, and you tend to feel, well, that's what cosmology is about. This is what is all established. But in fact, the cosmology sort of is a very active science. There are things which are not completely determined. What appears like a completely settled issue at one stage can turn out to be completely wrong direction later on. So one just has to keep this in mind. And that is the reason for this brief perspective. So one of the things that we saw was that, in this brief perspective, was that in the early days, so between 1917 and almost till 1930, people only took two models of cosmology seriously. One was due to Einstein and the other due to de Sitter. And it's important to know that in both these models, universe was the topology was S2 cross R, and there was no Big Bang singularity. Right? In both these models, there was no beginning of the universe. The universe was completely infinite. So this is why I, sort of in an amusing way, I read to you the story from 6th century BC when people were already worrying about whether the universe is eternal or not eternal. So Einstein and de Sitter would say it is eternal. But then we saw very soon after, Friedmann and Lemaitre independently actually realized that, showed that Einstein's equations had these solutions in which there is a Big Bang singularity. And as I told you before, that Einstein first dismissed this as an error, but then realized that it was consistent. But till 1934, so really this was a 17-year period between 1917, when Einstein and de Sitter discovered their solutions, till 1934, when Hubble's discoveries were kind of widely accepted, that the whole model of the universe was, people were completely wrong models of the universe. Then after that, the universe, one realized that in fact there is actually an expansion, right? The universe is undergoing expansions up here. And so, and then it also follows that the universe did begin with the Big Bang singularity, little a equal to 0, right? So that's what we saw. But even then, we're in 1934, so the Hubble discovery. And then Einstein acknowledged that in fact the universe is expanding and it is not static. The static solution was not correct solution. I should also add that Einstein was so ahead of his time and everything, but one of the things that he did not do, which is very surprising, is to check stability of his solution. It can be a homework problem almost. You can look at the stability of this solution. One can show that Einstein's solution is very unstable. It's completely unstable. It is really very delicately balanced between the repulsive force of the positive cosmological constant and the attractive force due to matter density. And if you perturb it slightly, it is not stable anymore. And it is very surprising that Einstein, when he had done so many checks and so many things beforehand, somehow did not do the check. Okay, so then after that, at least after this, then these Friedmann-Lemaitre models. That I mentioned last time, they became at least accepted as a potential candidate, but still they were not taken very seriously. And in particular, there was the British school, which was led by Fred Hoyle and Hermann Bondi, the same Bondi who we discussed about Bondi energy and everything. So Harman Bonji, so it's interesting that over there, he was right on target, but over here, he really thought that in fact, the universe was not dynamic, and then also Sharma, there were several people. So this was called the steady-state universe. So they tried to go back to this original idea of Einstein's that the universe is static, that the universe is not really evolving at all. Now, we just saw that if you had a perfect fluid, then in Einstein's solutions, Einstein's equations just imply that you cannot have, without a Gaussian constant, that you cannot really have a static universe. So this, in the steady-state universe, Einstein's equations were actually violated. It's very incredibly bold. Yeah, Einstein's equations were violated. And there is a continuous creation of matter. So stress and intensity is not conserved. And because it's continuous creation of matter, if you like, even if the universe were expanding, if matter is continuously created, then you can still have steady state at any given plane, location. The geometry and the matter and matter density will not change in time, right? Because you're just violating the conservation of energy up here. But this model was taken seriously by many people because somehow philosophically people felt it was much more satisfactory to have a model, a cosmological model, which is really time independent, which is the universe doesn't change in time. And there are a lot of astronomical observations which slowly cast doubt on this model, but really leading people were really supporting this model for quite some time. And it was really around 1965 that this model then became disfavored, and this came from two completely different directions. One is nucleosynthesis, and this was led by George Gamow and his school. So Alpher and various other people up here. And the second was the cosmic microwave background. So let me just say in a few words what this nucleosynthesis point was. That the point was that by then people had understood basic nuclear physics and various radioactive decays and these processes via quantum mechanics, which was quite developed obviously by this time. And so people knew that in fact stars were shining because of nuclear reaction. Now this is a huge leap, right? I mean, people literally till in the last century, right? The century before that, in the 1900s, in the late 1800s, the beginning of 1900s, people, the only way that they could see why the stars could be shining is because they thought that there was coal which was burning, right? And it was chemical energy that was being chemistry, not, in other words, chemistry has to do with atoms and molecules, and nuclear physics has to do with nuclei. And the chemical energy that is irradiated is not so efficient a process. And in fact, people quickly calculated and said that, well, if in fact the stars have been burning away coal, then by now, that coal would have all been burnt out. I mean, it would not be there, so to say. And therefore, in fact, the stars must be younger than Earth. And this was a real issue, right? Why is Earth so old and the stars are younger than Earth and whatnot? And because there was no physical process that was known which could make this star shine. And then when the radioactivity and quantum mechanics came along and people realized that this could come from nuclear processes, and they realized that the nuclear processes are much, much more efficient in converting matter into energy than, for example, the chemical processes. And therefore, people began to realize that, in fact, the stars are shining because of nuclear processes. And particularly Hans Bethe, but many other people, worked out the cycle, what is happening. And as you all know, in our sun, the sun is shining because we got the hydrogen is getting, it's a fusion, hydrogen is getting converted into helium. And in that process, huge amount of energy is released, and that is why the sun shines. So then people slowly realized that these, they worked out very systematically. They're all very exciting times, they're puzzles, they're solved and so on. People worked out that in fact, these nuclear processes would convert the lighter element to heavier elements, and so on. And so they realized that in fact the heavy elements that we see around us are probably produced by stars. That's in the star. But then very quickly it became clear that there was also an observed abundance of lighter elements, hydrogen, helium, lithium, and they realized that these elements could not have been, this abundance could not be explained if you assume that they're all produced in stars. Okay. Now I really want to emphasize that this is the kind of transition that one makes in science from qualitative ideas to a detailed picture which has to fit together in different ways. So they worked out the nuclear processes, they found the rates, they found and then the nuclear abundances that should be around, and they realized that the heavy elements, I mean the lighter elements, that is to say heavier than hydrogen, but lithium, helium and lithium and so on, they could not have been produced all in stars. So the problem here was that the observed abundance of light elements could not be explained using nuclear processes in stars. So basically what one is saying is that in order to make these heavy elements you need a hot oven, or heavier than helium, heavier than hydrogen, you need a hot oven. And the statement was that stars are really hot ovens, they cook these elements due to nuclear processes, but there are not enough of them to actually account for helium and lithium, the very lighter elements. And therefore the idea was put forward that the only way one could explain this is that in fact there was, in the universe, even before the stars were formed, there was a very hot phase, right, in the universe, in which these elements were cooked. So this was the idea. So the idea up here was really that the nucleosynthesis, the idea here was again that the light elements were formed in the very early universe. And a popular account of this is given very nicely in a very old, by now very old book by Steven Weinberg, which is called The First 3 Minutes. That this really will happen very, very early in the history of the universe, this nucleosynthesis appeared. So that was the idea, that there was a very hot phase of the universe, which is not there now, which of course contradicts the steady state idea. The steady state idea was that macroscopically there wasn't a hot phase and it's not cooling down, but it's just always there. And the second thing was this cosmic microwave background. And people realized that if you believed in the Lemaitre, in the Friedman and Lemaitre models, then in fact there would be an epoch in which matter and radiation would decouple from each other. And when the matter and radiation, so in a very early phase, the universe would be very hot, and therefore electrons, protons, and the matter, they are all completely together, right? It's a soup. But then the statement is that the photons escape out, and matter just stays behind. And when matter stays behind, then there is a free radiation that goes out. And this would be a blackbody radiation. At the time it is emitted, it is really extremely, it's hot, because it corresponds to precisely the epoch at which the matter and radiation decouple. But the statement is that as the expansion, if you take the Friedman model seriously, then this cools down. And then people estimated what the temperature should be now. And this was a long study, starting from 1960s. And this was sort of started basically by school around Dickey in Princeton. There are several other people, but this is the same Dickey, Robert Dickey, who was also was the Brans-Dickey theory Dickey. So he actually systematically, that his group systematically understood that there should be this blackbody radiation and that should be cooling down. And people took a long time to work out what the temperature should be now. And now, as you all know, it is about 2.73 degrees Kelvin today. So this is the prediction that was made, that came out of this detailed analysis. And then around in the mid, just before this actually, Penn, GS, and Wilson actually saw this in the sky. And so this was a big support for this Big Bang model, the idea that the universe in the beginning was very hot and then began to cool down, and therefore it is not steady state at all. And this was, so to say, the decline then of steady state theory. But I should say the steady state at that end, I mean, particularly, well, there was also gold, I should say, tiny gold. This actually continued for quite some time, well into the 80s and so on, but more and more people fell out of this idea, and then people realized that the Big Bang model that we use today is probably the accounts for the observations much better than the steady state model. But still, the statement is that observational cosmology was in infancy. I mean, typically people didn't know the Hubble parameter, for example, the value, there were controversy, and there could be of a factor of 100%, right? It could be 55 in some units or 110 in some units. I don't want to specify the unit, but there was it was not precision science at all. There was a lot of uncertainties, and therefore, this was not in the cosmology was not in the forefront at all. And what brought it to forefront was the exquisite experiment observations, particularly the COBE satellite measured the blackbody radiation very accurately. Not just that there is Penn, GS, and Wilson had just found that there is some residual noise that they could not get rid of. They were actually doing this work for engineering, whereas here the blackbody radiation was actually measured by the COBE satellite, and you've seen the curves many times. The error bars are tiniest, extremely tiny in the whole range up here, and so this became established up here, and then starting from here until then, as you know, that then there was a WMAP satellite. These are all satellites, and the final satellite was a Planck satellite. These three missions have provided us really precision observations, high precision observations, high precision results about our universe. So this really is the mixture of this theoretical development, which were there, which was right, but really the forefront came from these high precision measurements that happened. In the meanwhile, people have also done numerical simulation, large-scale numerical simulation. For the dynamics of the universe. And you have probably seen some of them actually showing how the universe evolved in many colloquia and seminars and such things. And to me, this is very striking, because what one starts with is these observations of the blackbody radiation. So these observations, when this decoupling took place, this decoupling, etc., in the standard models that we have with the Friedman-Robertson-Walker cosmology and so on, this happened about 380,000 years after the Big Bang. Right? This happened at that time up here. And so, I mean, Big Bang as predicted by this model. So these are all theoretical predictions. I'm not saying that there actually was a Big Bang. I don't believe there was actually a Big Bang. But within this model, there is a Big Bang, and so we just talk about that conceptual framework. Okay. So the state, I mean, just like, we talk about the solar system, and we just don't worry about general relativity most of the time. We just use Newtonian physics. Those concepts are not right concepts, but nonetheless, they work very well. So similarly, in this era, for example, the standard cosmology is okay. So we just extrapolate back and say that, well, there was an event called Big Bang. Something else happened presumably there because of quantum gravity effects. But you start the clock there, and it is just called the Big Bang. So Okay. So then people have done these numerical simulations, and this is quite striking because what one can do is one can put inhomogeneities as the initial data deduced from C and B. So in 380,000 years ago, the universe was essentially homogeneous, except for one part in 10 to the 4. Right, this is really 100,000, so 10 to the 5. One part in 10 to the 5, 100,000. So these are tiny fluctuations in the cosmic microwave background we observe. And then what we conclude is that these tiny fluctuations are really density fluctuations in matter. Right? The matter density is not completely homogeneous, but in fact there's slightly perturbations there. Now, why these perturbations are there, we don't know. But let's just accept it's an observational fact. And then we use known physics, which is very rich. So, general relativistic perturbation theory, but most of the time Newtonian approximations are excellent. And then of course astrophysics, gastrophysics, magnetohydrodynamics. We use all that, and then we see how these inhomogeneities evolve. Evolution of these inhomogeneities, how they evolve. And what one finds is that in fact, as we can imagine, gravity is attractive. So if there is a slightly overdense region here, then it is going to attract more material in this region. If there is an underdense region here, then of course the material from this underdense region is going to fly away to the mean. Just because the gravity is attractive, because this gravitational nonlinearity is really what is driving this evolution up here. But when we put non-physics and we do evolution, we find excellent agreement. So numerical simulations are an excellent agreement with the observed large-scale structure. So the large-scale structure of the universe, really by known physics, there's nothing new here, really evolved starting with these tiny inhomogeneities. All we needed was the initial conditions when the universe was about 380,000 years or young, and now this is the universe, as you know, is about 1.4 billion years. And now the statement is that we just look at the large-scale structure, and that large-scale structure that is actually seen is completely in excellent agreement with the known physics. Now, of course, there are, as always in physics, people look at it more and more detail. Some people say that there are some issues that have to be resolved and so on. But by and large, the large-scale structures can be explained by using the initial conditions with the C and B. Now, to me, this is a spectacular fact. Okay. Why is it a spectacular fact? Well, this is the physics equivalent of the following thing. Supposing we understood medicine, particularly physiology, biochemistry, all the organic chemistry that is relevant to the human body extremely well. And so much so that I take a snapshot of a baby when the baby is 1 day old. And then there is this computer program, we just plug this snapshot in here, and the computer program generates and gives me the picture of the person when the person is 100 years old. Okay. Can you imagine how much biology, biochemistry, all these things one would have to know in order to predict what the person would look like when the person is 100 years old? But that's what we do to the universe. If you take the ratio of 380,000 years to 1.4 billion years, you'll see that it's really the same as 1 day to 100 years. And so it really is true that we have taken a snapshot of the baby universe when it was 380,000 years young, and we know enough physics and astrophysics and gastrophysics and magnetohydrodynamics and all these processes to be able to predict what the universe will look like today, and it is in good agreement. So this is another example of the fact that we are living in extraordinary times, and you should all be excited about this. I mean, people have been, that's why I started with 600 BC, right? I mean, 2,600 years ago. because people have been pondering about these problems, and now we are answering these problems with such confidence. And even more than that, and the last point that I want to make about the introduction is the following. And then even more than that, namely, of course, we are physicists and we are never satisfied with the status quo. So we are very happy that knowing what the universe looked like when it was 380,000 years young, we can tell how it evolved, what happened, large-scale structure. I should emphasize that in philosophy circles and some physics people also, they sometimes tend to think of cosmology as telling you what is happening in detail. And that's just not the case. A working cosmologist doesn't tell you what is happening in the detail. It doesn't say that, in fact, there is going to be a solar system here and the planet, so many planets here, etc. What it's telling you is what is happening on a large-scale structure or some averaged out. It's like predicting the behavior of a river. There are floods, and then what happens. I mean, you're not worrying about what each H2O molecule is doing, how they're interacting, and how foam is produced, and so on. No, we're just telling about what the course of the reverse is taking. The river is going to take. Right? It's like that. It's really the large-scale structure that we're talking about here. Okay, but still we're not completely happy because we said, okay, that's fine. But who created these inhomogeneities, right? In the early universe, we measured them, we're there, but do we understand theoretically the origin of these inhomogeneities? Origin of CMB. Actually, what we of course observe in CMB is a sphere, right? A distant sphere up here because light is coming to us. So it really is anisotropic. But then we're extrapolating and saying that, well, that means the universe at that time was of a certain kind. What I'm saying is that we're here, this time is running up here, and we are observing what is happening in our past light cone. So this is when the universe was 380,000 years old, young, and here the universe is now. And what we are observing is that this up here. So we're really looking at anisotropies, but from there, mathematically, using the Friedman model, we're talking about there are these inhomogeneities. There's nothing very special about this particular sphere. I could have been here, I could have observed. The assumption is this Copernican assumption that there's nothing special about us. And therefore, we can deduce what the universe is going to look like everywhere. And that is what is giving us this inhomogeneities. So origin of the CMB, of these inhomogeneities, one part in 100,000, tiny, but still, if these tiny inhomogeneities were not there, we wouldn't be here. Right? None of those, there will be no galaxies, there will be no stars, there will be no planets, and we would not be here. So these tiny inhomogeneities are essential, and then the question is, what is the origin of this? Right? How were they created? So this is what we would like to understand. What is the origin of the CMB inhomogeneities? And then the statement that we're talking about, that there are leading scenarios, there are various scenarios. They have changed dramatically over the last 20 years. I should say, if you go back, something which was in mainstream, which was discussed in Nature, is no longer discussed, completely dropped. So things have changed quite a lot. So what are the leading scenarios? Well, one common element in the leading scenarios, because there are some scenarios which are not among them, but what the cosmological community takes seriously as possible scenarios about what is the origin of these inhomogeneities. The common element in the leading scenarios is very interesting. It is that these inhomogeneities, they are tiny, one part in 100,000 fluctuations. The idea is, therefore, they are looked at as perturbations. So these fluctuations are really perturbations. These are small perturbations. Or the Friedman-Lemaitre models. So these are just small fluctuations in the perturbations up here. But the key point, and people have known about these perturbations for quite some time. But the question is, well, what is the nature of this perturbation? And really a striking development for me is that there is a consensus in the leading scenarios that these fluctuations, these perturbations, have to be described using quantum physics. In other words, quantum field theory in the Friedmann-Lemaitre models. So this quantum physics is kind of a new thing, relatively. People have studied perturbations, classical perturbations, because general relativity is a classical theory, so people have been studying these classical perturbations for a while. But the idea is that in the very early universe, we really have to describe them using quantum physics. So this is an idea which is sort of common to most the scenarios that are pursued by astronomers, by cosmologists, and we are going to assume the same thing. And then, why is this so interesting? Why is this so attractive? I mean, to me, it is just fascinating, totally fascinating. Because if you accept this, then the origin of this fluctuation is really, the answer is, the origin of this fluctuation is that these are just the vacuum fluctuations of a quantum field. The quantum fields which represents these cosmological perturbations. So we've got cosmological perturbations. These are, if you like, these are perturbations like what we studied in the very last part of gravitational waves. You know, gravitational waves were perturbations on Minkowski space-time, those perturbations. But there we looked at the perturbations classically. The new and essential element here is that these perturbations should be thought of as a quantum field. And furthermore, these fluctuations are just vacuum fluctuations, which cannot, we all know that we cannot even get rid of them because of Heisenberg uncertainty. If you looked at quantum electrodynamics, for example, then we got electric and magnetic fields, and they are subject to canonical combination relations, and therefore they are uncertainty relations. So classically, I could create a field, right, which has a precise value of electric field and magnetic field. That's what we saw all the time using Maxwell's equation. I got time-changing dipole moment, and what is the radiation coming in, and we calculate E and B all the time. And therefore, it's obvious that I could have a place where there is no electric field and no magnetic field. E is equal to 0, B is equal to 0. But quantum electrodynamics tells us, no, you just can't do that, because delta E, delta B is bigger than or equal to h bar by 2. That's a dimensional factors. And therefore, the statement is that there is no configuration which corresponds to the 0 electric field and the 0 magnetic field. In the vacuum, there always will be, the expectation value of the electric and magnetic fields are 0, but their fluctuations, the uncertainties, in other words, for the position operator, for example, what we calculate is the expectation value, and we calculate the difference between the expectation value of x squared minus the square of the expectation value of x. That fluctuation, the same thing we do for electric and magnetic fields, that is not 0. You cannot make that 0. Expectation value, yes, but the fluctuations we cannot. And these fluctuations are the vacuum fluctuations of these quantum fields, representing the perturbations or the Friedmann-Lemaitre Robertson-Walker model. And the statement is that the origin of the CMB is really that in a much earlier epoch, when in general relativity terms, very close to the Big Bang, right? There was in fact just these perturbations. The universe was, if you like, trying to be as homogeneous and isotropic as it can be. But Heisenberg comes and says, no, you cannot be completely homogeneous and isotropic because these fluctuations cannot be identical to 0. These fluctuations are there all the time in the very early universe. And then the statement is that they just evolve. But then the question is, how do they evolve and become, the quantum fluctuations take place at a tiny length scales, right? Whereas the fluctuations CMB we observe is really fluctuations over very large distances, right? Because it is out of the whole sky. whole sky at this time up here. These are very large wavelengths. So the question is, how are we going to observe these? I mean, the question is, how do these small wavelengths get converted to this large wavelength? And this has been kind of a mystery, is a problem. And then the final answer up here is that the mechanism for this conversion is inflation. Now, inflation is the leading scenario or paradigm to explain the origin of these large-scale fluctuations in the universe. It's seen in the cosmic microwave background. So the idea up here is that in the very early universe, we had these tiny quantum fluctuations which got magnified because the universe expanded nearly exponentially. This is all introduction, so of course we're going to see all this in detail. Near exponential expansion, which stretched these fluctuations to very long wavelengths. So typically one says that there was this phase in the very early universe where the universe went until about 60 e-folds of expansions. This happened very quickly, right, in about 10 to the 6, 10 to the 7 Planck seconds. So 10 to the 6, 10 to the 7 times the Planck time. So it happened very, very early, very, very quickly. Now, you see these numbers and they don't mean much. I mean, 60 e-fold, okay, 60 e-fold. But you say, what does it mean? So during this incredibly short interval of time, something of the radius of hydrogen atom is blown up to the scale of a galaxy, kiloparsec. So this is really spectacular, right? I mean, therefore, this is an extremely bold hypothesis that something like this happened up there. The second thing that I want to tell everybody, I mean, we're going to see a little bit more detail, is the following. That at the onset of inflation, we might ask, well, what is the matter density like? So the matter density, what is the curvature like? The onset of inflation. Well, if the curvature were a Planck scale curvature at the onset of inflation, then we wouldn't trust this theory because this theory is based on quantum field theory or a classical space-time. And if the curvature was Planckian, Planck scale, then this theory in which the classical background is not is not trustable. So the curvature is small compared to the Planck scale, but not too small. It is about 10 to the minus 11 or 12 times the Planck scale curvature, which is Planck length to the minus 2. So this is the Planck curvature. But of course, so the Planck scale effects of quantum gravity in this epoch of inflation are deeply suppressed because this is minus 11, minus 11, minus 12. So they're deeply suppressed by these factors, right? And they're huge factors. So we're never going to see them in our lifetime in the observations, this directly, these effects. Okay? The effects which actually took place during inflation, the quantum gravity effects during inflation, not before inflation, but during inflation, are completely, totally negligible up here. But still one might say, okay, but how much is this curvature? So we'll say, I mean, is that large curvature, small curvature? Again, it's good to put the numbers in. And the statement is that this curvature is about 10 to the 65 times the curvature at the horizon of a solar mass black hole. The curvature at the horizon of the solar mass black hole is huge if compared to what is curvature up here. Everything will be torn apart, etc. If the black hole is very large, as we saw, if it's 10 to the 12th solar mass in black hole, then of course the curvature doesn't have to be large, but for solar mass black hole it is heavy. So we're talking about curvature about 10 to the 65 times the curvature at the surface of a solar mass black hole. I mean, it's just mind-boggling. And so no wonder people want to say, really? I mean, we can actually talk about physics at their scales? This statement is, yeah, it's all consistent. It may be wrong, but it's not because of some inconsistency in there. Even though the curvature is so small, because it is so small compared to the Planck, curvature is so large, even because it is so small compared to the Planck length, Planck curvature, we can use quantum field theory quantum field theory in curved spacetimes, and using specific quantum gravity approaches like loop quantum gravity, we can calculate the curvature with the corrections. And of course, not surprisingly, you find the corrections are going to be about 10 to the minus 11, 10 to the minus 12 times, the 1 plus the effects of the order of 10 to the minus 11 or 10 to the minus 12. So these are, of course, not observed at all. There's no problem. So during inflation, this assumption that space-time can be taken to be classical is perfectly fine, even though the curvature there is about 10 to the 65 times the curvature at the origin. So I mean, this really, to me, is kind of takes a chutzpah, right? I mean, it takes like really a lot of courage and a lot of intellectual almost arrogance to say that no, we can tell what is happening in spite of these conditions, and it's all consistent, self-consistent. So that is what we're going to really going to be talking about. So in this course, the main point up here is just to not what I've told up here, but really this what is the origin of this cosmic microwave background in homogeneities. So we're not talking about late time cosmology, what happens between even what happens after the 380,000 years up here. We're just talking about what is happening, how to explain this cosmic microwave background in homogeneities using inflation. And at the end, we'll see there are also limitations of inflation, so what they are and what the current status is, what we understand, and so on. So this is this is the idea. The only thing that I want to talk about before we embark into that project is the following. So the idea up here is that if you look at the history of the universe or evolution of the universe, the statement is that around 380,000 or before, not all the way to the inflation era, but say before this, when the universe was say 10 years old to 380,000 years old, if you like, the idea up here was that the universe was really dominated by radiation. So the equation of state was omega is equal to minus 1/3 p, and the expansion rates were the ones that I gave yesterday. So it's expanding at t to the 1/2. Then the statement is that this decoupling occurred here, and then after that, the universe is dominated by matter, dust, taken to be dust, pressureless fluid. But then, most recently, the expansion history of the universe, or the matter content of the universe, is dominated by and this is something that we can actually deduce starting from the Planck data and so on, that this is what the expansion history is quite well described by these simplified blocks. Here it is dominated by the cosmological constant. So this is often called dark energy. So we often hear, you have heard it hundreds of times in colloquia and session, that we have got the energy budget of the universe. And the energy budget is supposed to be about 67% or 68%. This cosmological constant or dark energy, people say. And then about 28% is going to be dark matter, and about 5%, there are decimal points, I'm not writing down decimal point, is this visible matter or baryonic matter. And the point is that throughout the human history, we have been just talking about this 5% part up here. I mean, we're not worried about these two things at all. But I think I just want to emphasize one thing very, very strongly, that this is something that students particularly don't get. This is the energy budget today. Remember that rho radiation falls like 1 upon a to the 4th. Rho dust was like 1 upon a cube. And rho cosmological constant, we wrote down, it is just given by minus 8 pi g, minus 1 upon 8 pi g. Times plus 1 upon 8 pi g. Because of u. Yeah. So it's plus 1 upon 8 pi g times the cosmological constant up here. So this is just constant. It doesn't change the scale factor of the universe, it's just constant. So you can see when the universe is very small, A is small, and therefore it is dominated by radiation, then it's dominated by dust, and now it is dominated by the cosmological constant. So the statement is that it's not true that the universe was always dominated by cosmological constant. This is not the energy budget of the universe, period. This is the energy budget of the universe today. At early part, these things were completely negligible. This is what dominated. Then this is what dominated until recently, and now this starts dominating. Now in the cosmology literature, there are always things that are a little bit mysterious to me and to many of my colleagues. Namely, they say that, well, there's a real problem. And like, for example, there's a problem. Why is the cosmological constant so small? Now, I personally feel that, well, I don't see what a problem is, right? I mean, it's no more a problem than why is the gravitational constant so small? Why is the gravitational attraction between two electrons, or say 2 electrons, is smaller by the order of 10 to the minus 40 times the electromagnetic repulsion between them? Or in the hydrogen atom, if you like, proton and the electron up here. Well, I mean, it's a fact. It's a striking fact. If there is a theory which explains this from some first principles without putting it by hand, that of course would be a revolution. That would be a great leap in our understanding. That is comparable to what happened, for example, when the beginning of quantum mechanics, in the spectrum of the hydrogen atom, Rydberg had a constant. It was Rydberg constant upon n squared. Was kind of the energy level side. Rydberg constant upon n1 squared minus Rydberg constant upon n2 squared. This formula explains this level splitting. But what is Rydberg constant? Where does it come from? Well, the Schrodinger and the Pauli-Schrodinger model of the hydrogen atom calculated that number from first principles. And that, of course, is a big spectacular advance. The same thing is true here. If for some reason one explained why the gravitational force is so weak from some fundamental considerations, that will be a great advance. But it's not a problem in the sense that, I cannot do anything until I understand this. I know we have done a huge amount of work in gravitation, in general relativity, without understanding why this is the case. The same thing here. The cosmological constant is very small. Is that a problem? I don't know why this is a problem. People talk often in terms of what is happening in quantum field theory, but then there is a problem about the way that they do regularization, renormalization in quantum field theory. It is very eloquently explained. If you are interested in this thing, look up references by Stefan Hollands. That if you look at carefully from the point of view of the quantum field theory and correct way of looking at renormalization theory and regularization of operator product expansions and so on. In fact, if you do it that way, then you find that it's not that the cosmological constant is too small, it's actually too large. Not way too large, but a little bit larger than what one would expect from simple calculations of quantum field theory. So I just wanted to emphasize here that this cosmological constant thing, I don't consider it as a problem. Again, if anybody were to explain this value from first principle, it is going to be a huge advance in understanding of the universe, but it's not a problem in the sense that therefore we cannot do something. The second point that I want to make is that another thing that cosmologists often say is that there's a problem, there's a coincidence problem. Why is it that only about now the dark energy starts dominating compared to the other thing? There's a coincidence, and we have to explain it. And I just don't understand it, because you got an energy density curve. This is falling off like 1 upon 8 to the 4th. This is falling like 1 upon a cube, and this is constant. So I plot these energy density curves falling off. Obviously, they're going to intersect somewhere. And then after that, this is going to dominate because this is too small, this is too small. So they're going to intersect somewhere. So what is the coincidence problem? Right? I mean, these curves just intersect, and they intersect about now. Now you might, if you want to, actually I don't see any problem. And the fact that the curve, which is 1 upon a to the 4th or 1 upon a cube, say for the dust, is, if I plot 1 upon a, sorry, if I plot a upon here rho, then dust is going to fall off. Cosmological constant was very small, but there will be some value of a at which these two curves are going to intersect, and so they intersect here. So that intersects somewhere. So I don't know what the problem is. We want to explain exactly why this happened. This particular part of the, well, that's just because of the initial conditions or something. I mean, in other words, this is no more a problem than understanding why radiation domination to dust actually occurred at some time. It's falling like 1 upon a to the 4, so this is going to dominate another 3 times. This is falling like 1 upon a cube, so after a while this is going to dominate. This becomes too small. So to me at least, it's not a problem. So people here, you will hear about this. And then we are going to also discuss a little bit about inflation. That inflation originally was started with horizon problem, the flatness problem, and so on and so forth. And we'll see more detail that is that inflation doesn't really explain any of those things. So all these things, that every talk that you hear about inflation is somewhat misleading. Okay, that's the point around it. All right, and we're going to see this in some detail. Okay, so this is the first part, which is the introduction, and now we begin with the second part, and the second part is perturbations. So this is kind of a cosmological perturbation, and this is very brief. We could have spent 1 month of lectures. This was just one lecture, so to say, on cosmological perturbations, deriving them in great detail and understanding the gauge issues, subtleties, and all those things. We're not going to do that. We're just going to. So what is our goal here? So this is extremely very brief. Everything that I'm going to do, unfortunately, because of our time limitation, is going to be very brief. So first, well, understanding cosmological perturbation. But just keep in mind this grand picture that will motivate what we do here. So this is just a conceptual and mathematical framework we're building here to understand what are the cosmological perturbations. And to begin with, we're just going to talk about classical theory. So really going back, in which people were talking about classical perturbation. In the third part of this cosmology lectures, we're going to understand quantum field theory in these cosmological spacetimes. Then these classical perturbation theories will become, these classical perturbation fields will become quantum operators, and we'll understand what is the behavior of those quantum operators. And then the fourth part will talk about the ideas of inflation, and so how this general quantum field theory in space-time, in cosmological spacetimes, becomes more specific when you bring in the inflationary paradigm. And in the last part, we're going to study the observations and theory, the interface of observation theory. You calculate something from first principles, and then these are the ones which are seen in the sky. That is the problem. So please bear with me. Now we're just going to talk about cosmological perturbations for one lecture. So what are these cosmological perturbations? So the idea, so this is going to be motivated by inflation. So I told you already that from now on we are really interested only in this issue about origin of homogeneity. So we're not interested in what happened in late times, but we're interested in what really is happening much before this time up here, from the end of inflation or from the onset of inflation to here. So that's what we're really interested in. In this period up here, so before the CMB, the idea up here, so I just tell you this idea, I just throw it at you, and I cannot do better than that. Namely, the idea up here is that in this very early universe, the matter field that we got is just a scalar field. It is called inflaton because it is supposed to be the one which is driving inflation. But for most of the purposes, we could just take it to a scalar field, and and then this in a certain potential. In some potential field. So typically, one often takes the potential that was studied in great detail at the beginning was just a harmonic oscillator potential, right? So it was just the potential where I got V of phi and phi. So just a harmonic oscillator potential. V of phi is equal to 1/2 m squared phi squared. And n is a phenomenological parameter, which then we use the data from inflation to fix the value of this n. The idea up here is really the following. I drew this potential like that, but in fact, the potential is very, very flat in the sense that it really, if we have to draw it out accurately, I would have to draw something like this. So that it is really sort of growing very, very slowly up here. The value of n is such that this is growing very, very slowly up here. And then the point up here is that the scalar field in the dynamics, I'm telling you very heuristically just so that you understand why we're doing what we're doing. We're going to come back to this and do this properly. So the idea up here is that somehow there's a phase in the early history of the universe in which the inflaton rolled down this potential. But this potential is very, very, very not steep, the opposite of steep, right? It's very, very shallow. I mean, it's very, very shallow up here. And therefore, as the inflaton is rolling down, this is really a slow roll. That means its kinetic energy is completely negligible to the potential energy. And since it is rolling down very slowly, the change in the potential energy during an inflation is so quick that the change in the potential energy is completely negligible. That means that the total energy in the inflaton field is almost a constant. Right? Because the kinetic energy is almost zero and the potential energy is not changing very much. So during inflation, this potential energy, the total energy is just a constant. But we just saw here that if the total energy is constant, then Einstein's equations say that it is like a cosmological constant and the solutions are expanding exponentially. So this is the near exponential expansion. It's near exponential because energy density is not quite constant. If the inflaton is rolling down the potential, then if the kinetic energy is completely negligible, even then the potential energy is changing very, very slowly up here. And we have to take into account that, and that is why it's called almost exponential. So this is what it gives rise to an almost exponential expansion. Of the universe. So please just keep in that mind. And now we're going to, so this is what we had, this is the idea, and now more precise framework is that we just have Einstein's equations with a scalar field phi, and we're given some potential at the moment. Ultimately it will be this kind of a potential, but to begin with we just take this general potential up here. We'll put conditions on it when we do inflation. So I got this potential V of phi up here. And therefore, we got Einstein's equation, we just say GAB equal to 8 pi G times TAB, and then the equation for this is going to be equal to block of phi minus E prime of phi equals 0. So if V of phi is equal to 1 upon m squared phi squared, then V prime just means some actions. The prime here is not with the proper time, I just made d phi by d. Is it? Okay. So if it was this potential, then this will just be equal to m squared phi, because 2 will cancel out. So the usual block of phi minus m squared phi equal to 0. That is the massive Planck-Gordon equation that we'll get at. Except that we're looking for homogeneity and isotropy. So this is the background dynamics we're looking for. So this is the background. and then we're going to put perturbations. So today, I will have time just to talk about the background, and next time we will take on the perturbations completely. Okay. So we got homogeneity and isotropy. That means that we got this, and I'm just going to get spatially flat universe. This is the assumption we're making. If it is not spatially flat, you can do this analysis. I'll just indicate how to do it later. But just for simplicity, let's suppose take it to be spatially flat up here. Then I got the stationary tensor for the field. And the stationary tensor for the field, as you know, is grad A phi, grad B phi, minus 1/2 GAB times grad C phi, grad C phi. I'll just get confused with this sign. The plus or minus. Plus. So that is the stationary tensor. And so we're got this stationary tensor. So we are looking for energy density. So the energy density, as you know, is TAB times UAUB. This U is the vector field d by dt. It's just the proper time vector field that we had with homogeneity and isotropy gives us some proper time, and that is the vector field. This is the cosmological vector field, if you like. And this is often is a proper time, or sometimes called a cosmic time. So therefore rho is going to be equal to, and so this rho is going to be equal to UAUB. So from here I get phi dot square. Here I'm going to get UAUB. So that will be plus 1/2. UAUB is U dot U is minus 1. And then again I got here, I only get phi dot square because the spatial derivatives are all 0. So the spatial derivative terms don't contribute up here. So here also I got the time derivative and the spatial derivative. The time derivative comes with the minus sign. And the spatial derivatives are 0 because of homogeneity. And then I get here plus 2b phi. And therefore we can see that the rho up here is just equal to phi dot square, the kinetic energy plus the potential energy. Exactly as you would think it should be, the kinetic energy plus the potential energy. And now I can calculate pressure also. So to calculate pressure, I mean this is isotropic. In general, there could be pressure in the x direction, y direction, z direction, which are different from each other. But it's isotropic, so I can just take, say, x direction, or y, or z. So I just take this stationary tensor, and I'm just plugging into two vectors in the space-like vector, x direction, for example. Then I'm going to get here 0, because this is spatially homogeneous. Here I'm going to get minus 1/2, because x directional vector field, here is going to be just, normally just plus 1. And then here I'm going to get again phi dot square, right? Because the only thing that contributes from here is phi dot square. And from here I just get plus 2b. Something right here. See, so this change sign, yeah, so this is minus phi dot square, sorry. This is minus phi dot square because grad phi and grad phi is equal to the time component is a minus sign, plus I get here. So this is just going to be equal to 1/2 phi dot square minus df phi. So of course these are just constant, and these are spatially constant. These are only functions of time only, because of homogeneous and isotropy. So we see here immediately that indeed the stationary tensor that I got here, TAB, is of the type that we think about. If you expand this out, it is of the type rho times UAUB plus P times QAB or UAUB plus GAB. This is the spatial metric QAB that we wrote down, where rho is equal to the kinetic energy plus the potential energy, and P is equal to kinetic energy minus the potential energy. Okay, so that's what we get. So it's a perfect fluid, so everything we did before can be applied, and we can look at the evolution of this this field up here. Except that the point here is that rho and p are both functions of time. Previously, we just considered dust, where in that case also, sorry, I'll take it back. When we consider dust, rho and p were also functions of time, but what we had was the equation of state. The equation of state was always given by p equal to omega rho, and omega was taken to be constant. For dust, it is equal to 0. For radiation, is equal to 1/3. But here, if I write it like that, then the statement is that omega itself will depend on time, because there's no simple relation here which will just factor out and make it time independent. Okay, so that's what we had. So this is the background geometry, and then what are the equations that we have? So these are the equations that we have to perturb, and this is the background configuration that we have to perturb. So we have to solve for the background configuration, and the background configuration, of course, is the metric GAB is equal to just gravity plus a squared of t times dx squared. That's our Friedmann-Robertson-Walker metric, and we got the scalar field phi. The scalar field phi up here, and then we saw that we got the Einstein's equation. It's only the time component of this Einstein's equation gives us the Friedmann equation, and the space component is only one because of isotropy, and that gives us the Raychaudhuri equation. So that's what we have obtained up here. So we get here a dot by a. Same thing that we saw last time. There's nothing new here. 8 pi g or 3 times rho, but rho now is 1/2 phi dot squared plus v of phi, and then a double dot upon a equal to minus 4 pi g or 3. And now I have to get here rho plus 3p. So rho is equal to this, and 3p is going to be equal to 3 times this. So I get here 3/2 plus 1/2, so I get 2 phi dot squared. And then I get here 3p, so 3 times this, so this is going to be minus 3 and plus 1, so it's also minus 2. Minus 2. And then there is a field equation, there is an equation for the scalar field up here, and under homogeneity and isotropy, that equation just becomes phi double dot plus 3h. H is just a dot over a times phi dot plus dv by d phi. Equal to 0. So we just have a minute or two. So these are the field equations that we get, these 3 field equations. This is the Friedmann equation, the Raychaudhuri equation, and the scalar field equation. And of course, it's a very nice exercise for you to check consistency. Because supposing I got this equation, Friedmann equation, I take its dot. Then the first term I'm going to get is a double dot upon a plus blah blah extra term. But I got a double dot, so I can substitute for that. Therefore, I use this equation, a double dot, and I substitute. So I use this equation. So I take a double dot up here. So a double dot by a. So I take dot of this equation. So I'm going to get here 2 times. 2 times a dot upon a times a double dot minus a dot upon a whole square is equal to 8 pi g or 3 times 1/2. Now I take dot of this equation, so that 1/2 goes away. So I get here phi dot, phi double dot minus d plus d phi plus dv by d phi. Phi dot. So I just take the dot of this equation and I get this. But now I can substitute for a double dot. This is double dot, it's not visible properly. I can substitute for a double dot this thing up here, so I'll get something up here. But here I got phi double dot. But phi double dot is already known to me. So this equation may be inconsistent with this equation. I don't know a priori it's consistent, but you substitute and check that it's all consistent. And the reason is, of course, because they came from a simple Lagrangian, and so you get a consistent system. But this is an important thing, that the Friedmann equation and Raychaudhuri equation you always have to check if they are consistent with the field equation that you have for matter. This, of course, in general relativity, everything comes, there's no problem. But very often, when you go to quantum gravity, these equations get modified. It's not so obvious that these equations are going to be consistent with each other. So you have to check that they are consistent every time. Okay, so these are the basic equations, and the solutions of these equations will give us A of t. Of course, that's not a unique solution. You have to give me some initial data, and then I can evolve. But it's a rather coupled equation, so it's not so trivial. Even for m squared phi squared, it's not so trivial. So I get here A of t, and then I'm going to get phi. So this will be the solution of the equation. And as we see, these equations are consistent. Therefore, I just have to solve two of them. And then if I can solve two of them for two variables, then the third equation is automatically satisfied. So that was the point that I was trying to make. That at first it might seem that there are only two variables, phi and a, and there are three equations. Are they consistent? And the statement is yes, they are consistent. Okay, so we get this background solution. So you get a background metric and a background scalar field up here, and then we have to take Einstein's equations and perturb them, and these perturbations will propagate on this background. So that's what we'll begin next time. We'll write down the perturbations. Once we have finished with the perturbations, we'll make a detour and just understand quantum fields in curved spacetimes, and then apply the quantum field theory in perturbation of curved spacetimes to the perturbations on this background. So these are the next 2 or 3 lectures that we're going to see. And the last lecture, we'll just put everything together and see how the observations data